Three,
2,
two,
1.
one.
Let's go!
First, introduce yourself. Give me a little elevator pitch, and then let's get into this.
All right. I am Molly Turco. I'm a structural geologist. If you're on LinkedIn and you do anything structural geology, you've probably seen these fun little Andy cubes.
That's right.
Yeah, if somebody wants to learn about like Ernest Mason Anderson and how we kind of came up with that, there's a quick little blurb right there. And then it kind of talks about the principal stresses, the magnitude and the orientation. And then those two things together, when they act on a rock, that kind of sets up for the fracture geometries or fault geometries that you can expect. And then if you remember, like mode 1 are your opening mode fractures, your like tension fractures, joints,
The orange lines.
veins. Yeah, and in the shear fractures, that's your mode 2. So that's like a shear fracture or a fault, whatever you'd want to call it. And then I do have little stylites on there. Those are, people call them closing fractures sometimes. But they're another like indicator of the stress field at which they formed.
You got to buy 3 of them
Yes.
in case you need to display 3 stress regimes at once. Talk to me about that.
So each of those 3 cubes is the same, but they're kind of laid out differently. The one on the left, that's a normal faulting regime. So in that case, S1, which is also sigma 1, that's your maximum magnitude of stress. It's vertical. So when that's vertical, your fractures pop open in S3 direction, your shear faults kind of open in that S3 directions. And the reason it goes in S3 is because that's the easiest stress to overcome. But because of that, your fractures and your faults are parallel with S2, which you can see right there.
Wow.
Now, there's a relationship. So when S1 is vertical, the angle of those faults are like plus and minus 30 degrees.
Okay.
As a geologist, we measure everything from horizontal, so that makes normal faults like at 60 degrees. But if you think about just sigma alone, those shear fractures or faults are at plus or minus 30 degrees to that. Turn that cube on its side, and now S1 is horizontal, but S2 is vertical. So that vertical overburden that's holding that down, that does not allow any rocks to essentially pop up, just in a very simplistic form. But you still get that same relationship. So S1 is still plus or minus 30 degrees to those right lateral and left lateral strike slip faults. They're still opening in that S3 direction. And then so that would be a strike slip faulting regime. And if you think about strike slip faults, we always think of those as vertical. That's because we're measuring them from horizontal. But if you measure from S1, they're plus or minus 30. And then that one on the far right is your reverse faulting regime. So once again, your shear fractures or your faults are plus or minus 30 degrees. And in this case, S1 is horizontal. So if you're measuring from horizontal, our kinematic orientation for thrust faults, we like to kind of just kinematically assume that's 30 degrees. That's just the simple way based on Andersonian faulting. But now that we're measuring from horizontal, it makes sense that that's why we see that 30-degree angle. And because S3 is vertical, that's why you get uplift when you get reverse faulting, because that's the easiest stress to overcome. So you generally need like strong compression, like continents colliding, orogenic belts, things like that developing.